Okay, so welcome everybody. 3 in the afternoon here in Brisbane, 4 in Sydney, some other fractional time in Adelaide and Northern Territory, and I don't know about Perth. So sometime earlier. So welcome to Unit 5 of the Mathematical Engineering of Deep Learning. You spent quite a bit of time with Sarat and Benoit, and now you've got me, Yoni, a bit back. So we've got 4 hours in this unit where we'll be speaking about convolutional neural networks, obviously. So we're here in the 18th hour. We're in the 15th hour of the course now. So we'll go for 2 hours today with a 10-minute break after 50 minutes, obviously. And we should be able to cover quite a lot of ground with convolutional neural networks. Just so you're aware, homework 2, the second and last homework, that's not counting the project, is up. So you can go and see the homework. Take a bit to read the 5 pages of homework. So if you haven't done so, perhaps don't do it now during the lecture. Important thing to keep in mind is that, as written up there, you are graded on the best 3 out of 5. So if you're time constrained, you don't have you don't have to do all 5 questions, but ideally you should. Certainly, to get the full comprehensive learning experience, you should. Quiz 1, who thought quiz 1 was easy? Just say yes, maybe. The chat is dead. And who thought it was a bit kind of tough with too many computations? Maybe say yes. Several yeses, too many computations. Yes, right. So yeah, we realized that it was kind of, that wasn't the intention, but just turned out that there's quite a bit of computations to do there. Georgiana, that's marking the quiz, will try not to reduce many marks or hardly at all on computation errors. And I see a question, what's happening with your grades? Your grades are being processed. So both the quiz and the assignment is being marked. I should say that the second quiz that's on in this coming Saturday is going to be significantly easier in terms of computation time. Okay. Yeah, so you'll know the grades of the first quiz quite quickly, I hope within a day or two. Okay, any other questions before we move on? That was kind of the administrative spiel. And most importantly, I think the Apple Pen is working. Last time you met with me in this forum, it wasn't, and it should work. Okay, so we're in convolutional neural networks, and what I'm going to do is I'm just going to jump from the web browser to Notability, where I can write on a screenshot of the website. So you can't see this video now, but that's this video about Chaser the dog. The dog, I hope you had a look at it. The dog that can recognize 1,000 stuffed animals. Kind of like convolutional neural networks can recognize 1,000, well, those that have been trained on AlexNet can recognize 1,000 types of labels. So just to see this happening, you've seen this at the start of the course, but I want to see it again because today we'll understand the machinery that's kind of underlying this type of thing. So what I'm doing in this cell well, now 12, this in 12 is preloading a pre-trained network, which is a convolutional neural network. You'll learn today what that is, and loading some image. You've seen the same image before, but we can put any URL of an image. And when I ask the network to classify the image, it gives us the label Granny Smith. Okay, so this pre-trained network has weights that capture about 0.5 GB of data, quite a lot of weights. It takes about 4 or 5 days to train on good GPUs, so it's not something that I can do on my laptop. But it's already pre-trained, and it does pretty much the same thing that Chaser the dog can do. And that thing, this didn't exist. I'm just going back to the iPad. This type of technology didn't exist a decade ago, and now it does. And that's probably the reason that we're here. I mean, deep learning has done variety of things, but um, convolutional neural networks were really the thing that drove deep learning forward. Okay, so the way we're going to present things is in convolutional neural networks is going to be slightly different. This is a mathematical engineering of deep learning. That's the title of the course, and it's going to be slightly different than the way that deep learning is presented in a variety of other online courses. So specifically, we're actually going to start just with convolutions and background on convolutions, just to kind of unpack this word and get a mathematical understanding for what a convolution is. Many of you have worked with convolutions, but perhaps you worked with in one sense and not in another sense. So I just want to unpack the meaning of convolutions just a bit. So for this, we're actually going to go back to something called the theory of system theory, or linear time invariant systems theory. This is often studied in engineering, but also in other contexts, in functional analysis as well, etc. And it's actually not so complicated. So we could understand what that means rather quickly. So for starters, let's just think of this thing that we call a system, okay? And when we think about a system, let's think about a box, okay? The system is just going to be a box where we put in some input signal, and let's call the signal a signal of time, okay? So it's something like this, but later on it'll be an image or something else, and we get out an output signal, y of t. Okay, but importantly, the system is not just a function that takes x of t at some time t, it actually takes a whole signal. So maybe instead of writing x of t, I can put, it gets x dot and gives us y dot, okay? It can be a smoothing operation, an averaging operation. It can be something that happens on the input signal and gives us an output signal. So this is a system, okay? This is a system. And mathematically in the notes, we denote the system by this kind of calligraphic O. It's an operator that operates on an input signal and gives us an output signal. So y dot for any time, say, is the system. This is a system operated on by x on x dot. Okay. Sometimes we just write this t here, but that's not so important. Okay. Alternatively, we can say that y at time t is the operation on the system at, well, sorry, that's just y. Okay, that's y. All right. Now, systems are many and varied, but one class of systems that's very natural to consider is this class of system that we call linear time invariant systems. Okay, linear time invariant systems. And when you'll see the definition, as you've already probably read before, it's not very surprising what linear is. Okay, so a system is linear if you put in a superposition, a linear combination of two signals, a weighted linear combination of two signals. So here alpha, alpha 1 and alpha 2 are scalars, and we're doing some superposition of two signals scaled by these alphas, okay, linear combination, then what we're going to get is the linear combination of the two outputs, okay? So this linearity is a combination of additivity and homogeneity, okay? That's linearity. Of course, if your system was just a vector, okay, if your system was just if your signal was just a random vector and your system was a matrix, for example, multiplication by a matrix is a linear operation, just as an example. Okay, but this works kind of more generally. Okay, so these are linear systems. And it turns out that in the world of signal processing, which is actually the precursor to convolutional neural networks in a sense, linear systems were critical because many things are described by linear systems. Actually, you've actually even seen, for example, a linear system implicitly in some other context. For example, just if we move to, I'll just move very quickly to unit 3, to optimization algorithms, and fly down here to say gradient descent with momentum, okay, or its more advanced version, which is say the Adam algorithm. okay, but enough to think about gradient descent with momentum. So if you look at this operation here, okay, that's the operation that takes as inputs gradients, okay, gradients, I'm just going to place it at the top of the screen, okay, so gradients are the input signals and momentum vectors are the outputs. You could think of it like that. So this system, which is actually doing exponential smoothing, is one example of a linear system, and it's also going to be time invariant, okay, but many others follow. So this is not the standard example in signal processing, but it's actually the standard example in time series. It's kind of a smoothing filter, okay. So that's what makes a system linear. Now a system is time invariant if the way it operates, the workings of this guy, of this O guy here, what's happening inside it, don't change when we change t, okay? So it's not operating different at day, at night. But to say this more mathematically, what we mean is that if we were to stick in a time-shifted version, okay? So when this is a time-shifted signal, okay? So what does it do to a signal when we subtract it by some constant tau? Does it delay the signal or preempt the signal? Where is the signal shifted? Who has an immediate intuition for this? So we had a signal x of t, but we actually are now doing x of t minus tau. Tau is, say, 10. Okay, so let's say the signal is a step. What is it doing? Is a step going to be delayed, or is a step going to be preempted? It's a delay, right? So as said on the tag, that's a delay. Okay, that's a delay. But of course, if tau is negative, then you're going to preempt it. But anyway, this is a time shift. So a system is time invariant basically if you stick in some time shifted input, okay, then your output would just be the time shifted output associated with the input as though you didn't do any time shifting. Okay, so think of a system that I kick at time 0 and it does something. Okay, if the system is time invariant, even if I kick it an hour later, I kick it, it does the same thing. It only starts an hour later. So these two properties, one or two, are very natural, okay? And of course, not all systems are linear time invariant, okay? But many systems are. Many systems are. The exponential smoothing example that you saw with momentum is, and so are many others, okay? So that's that. Who's heard about LTI systems before? Just to get a kind of a feel for maybe some people from engineering. So I actually don't see any yeses. That's interesting. Okay, I see some yeses. Okay, I see a yes. All right. So now it turns out that LTI systems are intimately related with this thing that we call a convolution, which we're going to see in a second. Okay, so that's LTI systems are. How do I make this disappear? Right, I've done this before. Nope. Nope. Okay, never mind. All right. So it turns out that LTI systems are intimately related with convolutions. And for this, we need to use a little to see this. We're actually going to prove this. It's not so shocking, but let's prove it. And it is highly celebrated in the study of LTI systems. What we need to do is we need to use some accounting trick. And for this accounting trick, let's denote this function delta t as as this function that actually is this function, I mean function of time, and it's discrete time, okay? So this is time 0. So delta t is going to be 1 here, and it's going to be 0 everywhere else, okay? That's delta t, okay? In continuous time, this is called a Dirac delta function, and it's actually a bit more mathematically delicate to describe, but in discrete time, it's just a sequence that's 0 everywhere except for 1 where it gets a 1, okay? So if you do that, then you can observe that delta t minus tau is a function that is 1 at the given time tau and 0 anywhere else, okay? And then what you can do is you can do this very naive, elementary, basic, but somehow useful representation of your signal. So now take any signal x of t. So basically you can say x of t is going to be a sum of this infinite sequence of terms, Okay, but how many of these terms are for a given t are not zero? How many of these terms here are not zero? Just a single one. Just the term for tau equals t, right? So it's a way to actually represent x of t as a infinite combination of scaled versions of these deltas. Okay. But once we do this, it's kind of useful because let's see what we can do now. And let's assume now that we have an LTI system. Okay, we have an LTI system. So, with an LTI system or with any system, we just denote the output of the system at time t is the system operating of x of t. Just to be careful here, what I actually mean is I could have put a dot here and put a t, okay? So it's a system operating on the whole signal and the output of that operated at t, okay? So that's what's written here is kind of slangish, it's not O is not just operating on the value x of t, O is operating on the whole input signal, okay? And this is evaluated t, but that's fine. So now that we've represented x of t this way, let's just stick that into our system, okay? And now let's use one of the two properties that we postulate for the system. Let's use linearity. Let's use linearity. Now, the system is linear with respect to, so it's looking for constants here that are independent of the argument of the function that we're putting in. Now, the argument of the function is t. It's not tau. Okay, the argument of the function is t. That's the argument of the function. So these guys, which are highlighted in green, these are constant with respect to the system. The system just treats them as an alpha, if you'd like. So then it can pop them out. Okay, and once they pop out, then you pop the system in. Okay, so that's linearity right there. Okay, that's linearity. Okay, now let's use a time invariance property. And for this, let's consider the operation of a system on a very specific signal, and that signal is again going to be just the delta function, just a delta function. So let's assume that when we put the delta function into the system, the delta function is this guy. If we put into the system something that's always at rest, always zero, except for zero, it's going to be one, and that's it. Whatever the system records as output is this thing. And this has a big name in signal processing, and it's called the impulse response, because it's the way the system responds to the impulse, okay? It's one description of the system. We'll actually see that it actually characterizes the system, but that's the impulse response. By the way, all this is actually quite general background for convolutional neural networks, so don't stress about it too much because we're going to depart from this soon. But at least here you're getting kind of convolutions 101. So as mathematicians, you're coming to a convolutional neural network, you're kind of having a feel of, well, where does convolution come from, at least in the general sense, okay? In case you haven't seen this type of thing before. All right, so the operation of the system on delta t is going to be h of t, that's the impulse response. Now the system is time invariant. That means that if we stick a shifted delta t, we're going to get a shifted h of t, okay? Right, because kicking it at time zero and giving it an impulse at time zero and seeing how it's behaving is the same. Well, you could just take that behavior and shift it by tau. That's a time invariance. Okay, that's how time invariance works. And then that means that this term here is h of t minus tau. So all we did here was, in a sense, an exercise which allowed us to describe the output of any linear time invariant system as this operation between, I'll highlight the input in yellow, and the property of the system in purple. Okay. Now this thing is called a convolution. And there's a question, if or Sarat saying something, if delta t is input, h of t the output of the system. Yes, yeah. So h of t is the output, the impulse response is the output to the impulse delta t. Okay. Now this operation is called a convolution. And you might have seen convolution in different contexts, in different ways. You might have seen it written like this, for example, for continuous time, Okay, you might have seen it first in the course of probability when you're summing up two independent random variables. You might have seen it in the context of differential equations, or you might have seen it in the context of multiplication polynomials. But one way in which the convolution, this operation between the two signals, the signal x and the signal h, occurs naturally is in linear time-invariant systems. Okay. It also tells us, if we just stay for a second more with this system theory, with linear time-invariant systems, it's kind of interesting that a linear time-invariant system, is just characterized by one signal, its impulse response. Like, if you know how the system responds to the impulse response, you know how the system responds to any signal. So stick in it some x of t, it's just a convolution with h. Okay. And in general, when you see a convolution, you see some sum here or some integral. And maybe that sum is going to be over some more complicated domain than just a sequence of integers. Okay. And it's important that you see one function here multiplied by a different one, where this one is flipped. Okay. It's flipped because you treat h as a function of tau. In this case, it's flipped. You've flipped h. And for any t, what you do is you run this summation. Okay. Now, has somebody watched this video? You can't see it here, but this is this kind of cheesy video with a few where English is not perfect, but that okay is. So that's this video. So if you haven't, I recommend watching it. Let me just highlight it here. I'm going to the browser, going to highlight it. That's just a video that illustrates how a discrete time convolution is a sum of flipped signals. So I recommend watching this. That's this one. Okay, that's this video. Okay, it's basically just treated as a quick animation. All right. Now, just a comment about convolution. The convolution operation is commutative, meaning that it's not hard to show. I'll skip the details, but they're written out here in detail. By just doing a change of variables, you can see that the convolution of x and h is equivalent to the convolution of h and x. Okay, so the convolution takes these two signals or two functions, two sequences, and do that. Okay. There's a question, shouldn't it be h of t as the output of O delta t, like the statement in time invariance property? Yeah, h of t is the output of, so h of t is the output of delta t. Okay. And yeah, so that's what's said here. Okay, that's said in slang here. Okay. All right. Okay, so I'm saying the convolutions are commutative, but let's just do a little quick mental exercise and define some other operation, which is not exactly the convolution. So we call it like the star with a tilde above. Okay, so it's just like the convolution, except that the sum is this and not this. Spot the differences between these two. Spot the differences. The argument of h, right? Okay, the argument of h. So this guy here, it's basically like the convolution of x in the flipped h, okay? Because it's flipping h. It's like taking the argument and flipping it in time. It's like doing h of minus argument, okay? In signal processing, it's actually called the correlation, okay? It's not exactly the correlation as correlation coefficient, but that's what it's called, the correlation. And this is fine, but just we're stating here that this operation is not commutative. Okay, so when you try and do the same trick here as showing commutativity, if you were to define your convolution like that, it's not commutative. Now, commutativity of convolution is important in classic linear systems, because what you're going to do often is you're going to have a signal x, and you'll stick it in one box, and then you'll stick it in another box, and then you'll stick it in a third box, and you'll get your output. And if all of these are LTI, then commutativity means that we could actually interchange these guys, and it wouldn't matter. Okay. Now, in neural networks, we're going to do something more. We're going to stick some highly unlinear wrench in the works. What's a non-linearity we stick in neural networks? What is it called typically? You're already graduates of the activation function, exactly. So once we're going to stick activation functions, then these things won't be linear anyway, and commutativity is not so important. And this is the reason that the convolutions that we use in linear networks, in neural networks, are actually going to be often these guys. We're not going to worry about flipping the signal really, but it doesn't matter. It's a detail. Okay, so. And anyway, our convolutions are going to be typically two-dimensional or multi-dimensional. So it's going to be some inner product of x and h, as we'll see in a second, but it's not going to be with this h, which is like this. It's going to be with this h. Okay, it's a bit of a subtle point, but all I'm saying is that the convolutions we use in neural networks are not bona fide proper convolutions. Okay, questions, thoughts? All right. So now convolutions also appear in the field of probability. So who's seen convolutions in probability? Let's just make us feel good a bit. Yes, in probability you've seen them. Okay, good. And how do you do a convolution effectively? Oh, a lot. Good. How do you do a convolution effectively in probability? Because convolution is hard. You need a sum or integrate. You can do like a characteristic function or moment generating function or probability generating function or Laplace transform, right? And then multiply. Right? And the same, by the way, for linear systems. Okay, but good. So you've seen convolutions probability. So I'll skim, or many of you have, I'll skim over this quickly, but that's just important that you kind of see that it appears in a completely different field. So the story is that if you're summing up two random variables, and it's important that they'll be independent, so you've got the random variable x and y, and you call their sum z, and you care about the probability distribution of the sum, then what you can do is you can use the law of total probability here and condition on, say, the values of y, and then what you get is exactly something like this, okay? And when you see something like this, you immediately see a convolution, okay? It's exactly using the notation that we had before, the convolution of the probability mass of one function and the probability mass of the other function. Probability mass functions, like density functions, some people call them, of discrete random variables. But this would also hold for a continuous random variable. Okay, so you've seen convolutions in probability. Good. So I just wanted to point out this convolutions in probability. Okay, I'll move on. All right. Now, convolutions can also be treated as the resulting coefficients of multiplication of polynomials. Has anybody entered the field of convolutions directly through multiplication of polynomials? Was this this is what a pure computer scientist would probably see. No, I don't see any yeses, any new yeses. Okay. So if you take these two polynomials, okay, and you take their product, okay, then you just expand terms, right? So the highest term is going to be this guy times this guy, right? And that's going to be a 7th order term, okay? And the lowest term is going to be this guy times this guy, but we're going to get quite a lot of terms, okay? So we can actually, I recommend going through this once, okay? And just seeing that the resulting polynomial is going to be a 7th order polynomial, meaning it has 8 coefficients, which has these terms. Now, if you look at each one of those terms here, it's actually the convolution. Well, the whole thing is a convolution of x and y, because the thing that gives us as a convolution, first of all, you're kind of multiplying cross terms, but then, you know, x is going up and y is going down in indices. Okay. So, and of course, this looks very different than the LTI system. It looks very different than probability, but it's actually the same thing. Okay. In this case, one way you can write the convolution is you can just write it as this summation, where you're summing over the z at t, the t's coefficient of the resulting product polynomial is going to be a sum of product coefficients. And it's important that the coefficients here, there's some sum up to t. Okay, but this formula doesn't specify at all. You need to look at this paragraph where the sum is over ij pairs, where ij is t, and we don't go too far to the left and too far to the right, because we don't have like an x -3, right, and we don't have a y 25, etc. Right. So I mean, this was our data. We just have this. This is this and this. These coefficients. That was our data. Okay. Let me actually just pause here and speak about something that we won't speak of for the rest of the day. What's an efficient algorithm for convolutions? Somebody must have come across this. An efficient algorithm for such convolutions. I mean, don't say out the algorithm. Maybe say the name. We got FOIL. We got FFT. Okay. Oh, so FOIL is the high school method that would do here. That would have if this is a polynomial of order n, this is a polynomial of order n, then you've got like n squared steps. But FFT, what does FFT stand for? The fast Fourier transform, which is an efficient implementation of the discrete Fourier transform, is actually able to do it in n log n steps, okay, which is in an order of n log n steps. Okay, so the whole concept of fast Fourier transform, which has done to the world probably more than deep learning so far. Maybe deep learning will go kind of fit, but this was invented in around 1965, and we're speaking now. Our voice is actually going through all kinds of fast Fourier transforms. I think I'm mostly speaking, but my voice is okay. Your text isn't going through fast Fourier transforms. Now, we won't speak about fast Fourier transforms in the context of convolutional neural networks, but there is literature that intertwines FFTs and convolutional neural networks. So there's things to do there, but it's not immediately obvious how. Okay, so one cannot speak about convolutions for half an hour as I did and not speak about the fast Fourier transform. Okay, all right. Now, here's one more thing about convolution. So, and it's easy to see it when we look at it in the context of these polynomials. So look, we had here our inputs. Let me erase this big mess that we did here. So our inputs were these coefficients of x and coefficients of y. Okay, these were the inputs. And the outputs, the result from the convolution, were these coefficients of z. Okay. Now, we can also get these coefficients of z by getting the coefficients of y as, say, an input vector that is operated on by this matrix, which has the coefficients of x. Okay, so the coefficients of x, let me just paint this, the coefficients of x, we're being color consistent at the moment. Okay, and these are the coefficients of y. Okay, up to y5. All right, so you've got y0, 1, 2, up to y5, etc. And you could just see how this works. I mean, you see, let's just take this row, for example. Okay, so this multiplication, I should maybe do it like that. So z2 is going to be the inner product of this row and this vector. Okay, so y0 times x2. You see, y0 times x2 is this element. Okay, and then y1 times x1. Okay, y1 times x1. The third one is x0 times y2. All right. So that's kind of nice that we can represent the convolution operation as and this is now a convolution over some finite vector here. Okay, as a multiplication by a matrix. And this matrix in general is called a Topless Matrix. Any matrix that has band diagonals that are the same are Topless matrices. Okay, so that's a Topless matrix T of x, which implies that if you apply some vector y to T of x, you get the convolution of y and x. Okay. And of course, since convolution is commutative, you could have flipped. You could have, instead of T of x, taken a T of y and then apply T of y to x. Okay. That's kind of important. So convolution is a linear operation. And in neural networks, so when Benoit taught you, went with you about on unit 2 and unit 4, it was all linear operations, except for these little activation functions. Okay, that kind of make everything more complicated, but at the same time more powerful. All right. So keep in mind the convolutions are linear operations. Okay. So performing a convolution is at least mathematically just like multiplication by a matrix. Okay. So this is pretty much what we're going to say kind of on convolutions per se. Any thoughts or questions? All right. So now let's get to the key idea of a convolutional neural network. Okay, the key idea. And for this, let's depart just momentarily from convolutions, and let me just give you some example of some silly hypothetical neural network here. Okay, this is not something you do in practice because this example, which I'm going to show, because the example is a neural network that works on what is it? On 1 million sound samples. Okay, so you've got a sequence of 1 million sound samples. And just to put it in context, if you have 1 million sound samples, if you're sampling at a rather standard rate of 8,000 samples per second, that means a sample every 125 microseconds, which is 125 seconds of voice. Okay, so 125 seconds of voice recording, uncompressed and with no smart things happening, is roughly 1 million sound samples, a vector of length 1 million. Okay, a vector of length 1 million. Now, of course, we're not going to use neural networks on vectors of length 1 million of voice. For this, you'll meet Benoit in Unit 8, I believe, in the sequence models unit. Yeah, Unit 8 here. Okay, the sequence models unit. That's where you're going to deal with this. But let's just treat this hypothetically as an example, just to motivate the things. So imagine that we're just doing binary classification on this vector of length 1 million, which is a voice recording, and our purpose is just to know if this is what is it? If it's a human conversation or other sounds like birds or whatever. Okay, human conversation or not, just binary classification. I mean, that should be pretty easy to do. I mean, that's a classifier that, by the way, works all the time when you all the devices that are listening to us run this type of classifier continuously on us. Now, I see a statement on the chat which starts with OMG. Oh, and then it says, oh, don't mind me. ODMM. That's oh, don't mind me. No problem. Okay, so I'll just enjoy. Keep using the chat. Chat is good. The good thing, you can actually chat in class, and it's allowed. All right, so I'll skip that. No problem. Okay, back to this thing. So now imagine that we have the following deep neural network for classifying this thing, and I wrote it like this, which is maybe slightly different than the way you've seen the networks with Benoit up to now, but not really. I mean, first of all, unfortunately, I wasn't consistent with his notation, which was better, which would have put a 1 in the superscript here and a 2 in the superscript here and a 3 in the superscript here. These are like the layers. Okay, these are the weight matrices, but that's not critical. But the point is that if you just want to describe to a mathematician what's a deep neural network, then you say, no problem. Deep neural network goes as follows. Well, you start with some vector x, where x is an R 1 million, and you apply on it the matrix W1 and add to it the vector B1. Okay, the weight and the biases of W1. Okay, and so that's an affine operation, what you'd call, okay? And then you apply an activation function, which we chose to be ReLU in this case. Okay, and then on this, you'd apply now the weight W2 and add the bias W2. So that's now almost the values of the second layer, the output of the second layer. And then you apply on this the another ReLU. Okay, so these are the neurons in the second layer. And then you go for the third layer, and you've got your, whoops, that's not what we wanted. You've got your weights W3 and your biases B3. And by this time, the network is actually designed such that W3 outputs a scalar. Okay, so outputs a scalar, and that's the output of the third layer. And then, ideally, you could have stuck it through a softmax or something like this. But here, I'm just going to stick it through a sigmoid. Okay, and if I do, a sigmoid gives us output, right? Between sigmoids kind of goes between 0 and 1. If I multiply by 2 and subtract 1, I get a positive 1 or a negative 1. Okay, and then the sign of that is, this is kind of one way of doing it. It's not a big deal. Okay, that's not the main point here. But the point is this neural network has quite a lot of parameters, okay? Of course, we can choose how many parameters it is, but let's just take something that might kind of make sense. So the input dimension of W1 might be a million. Well, not might be, it will be a million because that's what we said. We're working on a million voice samples. And this here was a design choice. You know, you have 10,000 hidden neurons in the first hidden layer. And then, you know, you take these 10,000 neurons in the first layer and you put them and you get, let's say, 1,000 neurons in the third layer. And then you go from 1,000 neurons to only to 1 neuron. And that's in the output layer. Okay, that's this guy. All right. So if you kind of compute how many parameters this thing has, it's this precisely, which is roughly this, and 10 to the 10 plus 10 to the 7th is about 10 to the 10. That's a dominant term. So it's like 10 billion neurons. Now, today's neural networks are trained with even more than 10 billion neurons. However, they're for much more serious tasks than just detecting if voice is human or not. Okay, and of course this was also very specific because, you know, this listened to 2 minutes of voice, but there was so much waste. I mean, neurons, you know, it should all be kind of time invariant, shouldn't it? I mean, you know, what I'm saying in the first minute is kind of like what I'm saying in the second minute, or what I'm saying in one segment is a different segment. This is so wasteful. So the idea of convolutional neural networks presented mathematically is simply, let's, instead of use these guys, now let's put them in some red circle, these bad guys here, let's replace these by Topless matrices. And Topless matrices, you know, they're just as big, but they actually have very low parameters. Look, this Topless matrix here, now this is a, this is a whole matrix, but its parameters are just these. Okay, the parameters are just the values of the filter. Okay, so that's kind of the idea of convolutional neural networks, or at least one of the ideas. So let's replace W1 by Topless matrix T1 of H1, and W2 by T2 of H2, and W3 by T3 of H3. The operator, the matrix TH, is not well defined by itself because we need to know what the output dimensions is, but these are Topless matrices associated with the H1, H2, and H3. So they're only oh, sorry, at least let's do this for H1 and H2. Okay, and we could leave the third one as we'd like. All right, so that's the idea. So the main point is one, reducing the number of parameters, but two is also using the fact that voice conversation over 2 minutes or an image that spans a whole screen, you know, might require the same type of operations in different locations of space or different points of time. And that operation can be characterized by, you know, just a convolution filter. Okay, here or here if you'd like. So that's roughly, that's one of the main ideas of convolutional neural networks. Now let's go here to the second key idea. Second key idea is using multiple channels. Okay. Now, again, I'm just saying, if you're watching this, maybe in retrospect or maybe live now, and you're also watching something else dealing with convolutional neural networks, and the typical way the convolutional neural networks would be presented would be, here's an image, let's process the image. Here, we actually prefer to speak first about voice vectors. So an input that's just a vector of a voice recording or a sound recording. Okay, so the second idea is this idea called multiple channels. Multiple channels. So here's the idea. And let me actually let me maybe draw for this one. So I'll get a blank page here. Sorry. Oh, I didn't get the blank page where I wanted. Doesn't matter much. Okay. So here's our input. Let me maybe draw it like this. Here's our, no, I'll draw it like this, not to confuse with the layer. This is the input signal, X, okay, input. In a standard neural network, what you do is you'd pass this X through the first operation, the first layer, and you'd get Z of 1. Okay. All right. And then you pass it through the second layer, and you get Z of 2. I'm purposely putting these kind of laying down as opposed to what you thought you saw here, just to not confuse with what's going to come forward. All right. Now, what we could have done is we could have taken X and we would split it into one copy here, which we'd call the first channel, and maybe a second copy here, which we'd call the second channel, and a third copy here, which we'd call the third channel. Okay. And the reason we would do this, and specifically in the context of convolution, so in a fully connected world, this doesn't make sense to really do this. So I've now just replaced this by this. Okay, that's what I've done. So in a fully connected world, this doesn't make much sense. But if what I'm doing on this X is actually running a convolution filter, then maybe this one was by running some very specific filter, this kind of orangey filter that does one specific thing, and I ran this filter everywhere. Okay, I ran it everywhere on X, and it came here. So that's the output of an orange filter. And maybe I have a different filter that does something else. And by doing something else, say if we're speaking in the context of voice, filters can reduce high frequencies, filters can actually sharpen the voice, filters can can smooth things out, filters can do all kinds of things like this. So let's say, here I had another filter and I ran this filter all over the network. Okay, all over the input data, and that's the second one. And then I've had like a third filter which does something else, and I ran that and got the third one. So now the data in my first layer is not as just it was before. It was a fully connected layer. Now it's kind of the output of 3 different channels. Okay, and then the idea is that I can run this again, and I can create another thing, which maybe won't just have 3, maybe it'll have 5 if we'd like. Okay, it might have 5 different channels. So we have 3 channels here and 5 channels here, but that's a design choice, and we'll speak about that, but that's in a sense kind of arbitrary. Now, I'll speak in a second of how I get to these 5 channels, but let's first just understand. So we've taken the filter and we split it into 3 channels. So let's see this thing mathematically. Okay, so we now have this new concept that you haven't heard about before in the context of fully connected layer networks, but in the context of convolutional layers, this concept is channels. Okay, and what it means is that you'd have this Z1, Z superscript 1, Z superscript 2, Z superscript 3 are mapping with channel 1, channel 2, and channel 3. And well, I didn't draw them in that order, but that's okay. And the 1 is like the first layer. Okay, it's layer 1, layer 1, layer 1. Okay. In each case, what we did, we applied, this is how we apply this Topless matrix, applies the convolution filter H11 on X. Here it applied the convolution filter H12 of X. Here it applied the convolution filter H13 of X. Okay, this was like the H1, the H2, and the H3. Okay, all associated with layer 1. Okay, so they're all subscript 1, subscript 1, subscript 1. Okay. Now, and in each case, we also have a bias term. That bias is just going to be a scalar. It's going to be the same bias for everywhere in this application. Okay, and we also run some nonlinearity, and the most common nonlinearity these days is ReLU. Okay, so we apply ReLU on that. Okay, so this is what we get up to here. So now we've got 3 different channels. And again, think of it in voice processing. If you were kind of a classic signal processing expert and you're taking voice, what you do is you might run 3 different types of voice processing to take the high frequencies, maybe to take the low frequencies, maybe to smooth things out. Okay, and that would be your 3 channels. But we want to go deep. Okay, I mean this course is about deep neural networks, and that's kind of where the things are. So we also get a second layer. Okay, and maybe a third and a fourth and maybe a hundredths layer. Okay, not a 10,000th layer. Nobody's gone to 10,000 really. Okay, yet we're in 2021. Okay, so what you do in the second layer is you don't just run now, well, let's draw some more. Let's choose some other colors. Let's choose these kind of colors for a convolution. So this filter here, which we'll call H2 for second layer 1, but we're actually going to use a capital H, and you'll see why. It's not just going to operate on this guy. It's going to go this way. It's going to operate across here. It's going to run all across. It's going to treat these guys as actually, it's going to crunch them together. It's going to treat them as one. Let me actually draw it. It's going to, this is the first. I'll just stick them together. Second and third. It's going to treat them as this one kind of chunk of matrix, and it's going to operate all across. Okay. So the filter is going to look through the channels, and you'd want that because, you know, if this was like the high frequencies and maybe the low frequencies and maybe something else, and when you go to a deeper layer, you actually want to involve elements from all three. Okay. And similarly for this filter, and similarly for this filter, etc. Okay. Now, this guy, a capital H, is no longer this kind of single variable function convolution. It's going to be a two-variable convolution. And actually, in images, we'll need volume convolutions, and we'll get to that soon. All right. So just so we see how the second layer looks like. So the second layer has, this is layer 2. And it might have multiple channels. Like here, we drove 5 channels. This is like 5 channels. This is channel 1 up to channel, yeah, say, for example, k equals 1, 2, 3, 4, 5 in the illustration, but not necessarily. Okay. In this case, its input is going to be the concatenated vector z11, z12, z13. It's all of this, okay, which is just the joining of these 3. And it's going to apply, it's not going to be just your typical Topless matrix like we had before. We didn't write this in this notes, and it's not so critical. It's actually going to be a block Topless, okay? It's going to be this bigger matrix T tilde, which operates on this filter H2K, which mixes all 3, okay? It's still going to have just a scalar bias, right? And that's going to be your second layer. And from there, you can continue, okay? Now, if we would have started, we'll take the break in a minute. If we would have started saying now, what's the equivalent in voice? If voice is a vector, you know, I want to go to kind of something that's a bit more than a vector. So I'm just asking you. So let's say in images, if a black and white image is a matrix, a color image is like a 3 tensor, right? It's like 3 matrices, RGB. What's the equivalent in voice, just in the world of voice? From what's the analogy? From monochrome, image, stereo. Somebody said it. Wonderful. Wonderful. So say we would have done, thank you. So say our input would have been, you know, X left and X right stereo. Then anyway, from the start, we're starting with kind of multiple channels. So what I want to say is that this notion of channels, you know, in the example we started with, there was no channels in the input layer. This is an input layer. Okay. This is just an input, okay? There are no channels. But if you go to stereo, there are, okay? And channels here don't necessarily have a physical meaning, but actually they have meaning of understanding what's in the network, and then we close off the network, and we'll see how that works. Okay, so that's what's in this section, and that was kind of the key point. And this might have been all very abstract, but we'll get back and just describe convolutional neural networks on images in a few minutes. Are there any questions before we take a break? Thoughts? Okay, so let's meet in 6 minutes. I've cheated you out of 4 minutes. 4 minutes, so 6 minutes in the next round hour. All right, so see you in just a bit. Bye.